Hello, everybody. In case you haven't met me before, my name is Caitlin. I'm a graduate student at West Virginia University. And today I'm going to talk to you guys about this new project that I've been working on with a few members of the astrophysics working group, where we're looking at capabilities and limitations of searches for supermassive black hole binaries and time domain surveys. So the main idea here is really just what kinds and types of supermassive black hole binaries are we capable of discovering in these electromagnetic surveys? And are there any kinds that we'll be likely to miss? And this can be really important knowledge for us to have in NANOGrav as we're preparing for continuous wave searches, as we might be gaining the sensitivity that we need to detect continuous waves over the next few years. And this is going to be really important as we attempt to do multi-messenger science and try and match the continuous wave gravitational wave emission to a potential host galaxy. So just a little bit of background knowledge. So AGN have an intrinsic red noise that can be described through a damped random walk. And I've made a few simulated light curves here on the right, just to give you an idea of what this looks like. So here we have time on the x-axis in MJD, and brightness and magnitude on the y-axis, and you can see the way that the brightness of these AGN varies over time. But both of these AGN that I've simulated only have noise in them, even though the bottom one looks very different from the top one. So this one is a little bit more flat and random, and this one really seems to wander. It almost looks like there might be some sort of periodicity in there. But all that's in there is the damped random walk, and that can be described through two parameters. So sigma is the variability amplitude, so how big is this variance, like in the brightness, and tau is the time scale of this variability, so how long does it take to return to zero after wandering away. So what we've done is we've worked on some methodology to recover these damped random walk parameters, similar to work that's been done in the past. So what we've done here is we've compared our methods of recovering these parameters from our simulations with some previous work, specifically Kozlowski et al. And you can see here on the upper two plots from their paper, what they were able to do is compare the input and output parameters that their search returned versus what they injected. And this is for parameter rho, which is just the variability timescale tau divided by the length of the observation. So you can see up here for very low values of rho, they were able to do a great job recovering it, both for a less densely sampled light curve, like in an SDSS style survey, or a more densely sampled light curve. However, once you got to very large values of tau or rho, they were able to recover it less accurately, and it was frequently underestimated. So it had this sort of like turnover effect up here. And you can see down here from our recreations that we see a very similar effect. So in middling or low values of rho or tau, we're able to recover it very well. But once we get up to high values, we frequently underestimate it. And the same statement goes for the more densely sampled light curves. So this is good that we can do a similar job to others have in the past. But what about the binaries? You might be asking me, Caitlin, why are you just talking about AGN? Well, we care about here in NANOGrav our supermassive black hole binaries. So a supermassive black hole binary can change the effects that we might see in a variable AGN. So even though there's a lot to study in the noise on its own, what we're really trying to look is how this interplays between a sinusoid, which might be hidden under the noise. So a nice plot that I like to show for this is this plot of PG1302 from Ting Ting's paper, because it does a really nice job of showing how complex this noise is on top of this possible periodicity that might be in the source. And this is the kind of thing that we're going to be simulating and looking for in this work. So as we're adding the sinusoids for this search, the ones we're adding right now are in simple parameters, just an amplitude, a period, and a reference time. But you can see an example here on the right where I've injected the plotted orange sinusoid into the noise that I showed before. And you can see that, again, it looks fairly similar, and it might be very easy to mistake this for noise, especially knowing what it looked like before and knowing that that was only noise. So this is a really complex problem, and depending on the realization of the noise, it can be really difficult. So luckily, this method that we've written and a lot of people have worked really hard on is able to do a really good job, and we're able to recover the sinusoid parameters really well. So here you can see I've plotted both period and amplitude of the sinusoid from injected on the x-axis and output by the MCMC on the y-axis. You can see they follow along a nice line. So this is great. This means that we're recovering both the period and the amplitude of the sinusoid really accurately. We're also able to do a very similar job when we're searching over the sinusoid parameters as well as the damped random walk parameters. So you can see here, this is the same tau or rho plot that I showed before, where we're able to do a very good job down here at low tau, but then we have this turnover where we're unable to recover the high values of tau. So this is good that we're doing the same as we were before with searching over the signal as when we're not. Another good thing to know is that when we only inject noise into that search that looks for a signal, we're able to characterize the noise just as well. So you can see we get the same exact behavior whether there's a signal or not. So the orange points have not had a sinusoid injected into them, but we've searched for one and we're able to recover the same noise parameters. So one other thing that we need to make sure we can do is do an accurate model selection and be able to tell whether we should be modeling a given light curve with a sinusoid or with just noise. And the way we're going to do that is with a Bayes factor calculated from a Bayes information criteria, or BIC. And you can see an example of this plot on the right. So you can see here, I'm plotting the amplitude recovered by the MCMC versus the Bayes factor that we calculate for the model, or for the given light curve. And you can see for very high amplitudes, get a nice high Bayes factor. And for low amplitudes, we tend to have a lower Bayes factor, but still not tiny. And these are all for simulations that have had a signal injected. And you can see also in the more dense light curves on the right, that these Bayes factors get really, really large, which is great because this will mean that it's going to be very easy to see these very strong signals. Another thing that's good to know is that when we do make the same plot when we've also searched over light curves that only have noise in them, we get very low Bayes factors for the noise-only light curves. And this is great. This is exactly what we want to see. But one good thing to notice is that for the left-hand plot, which has the less densely sampled light curve, so there's fewer data points, there's more of an overlap in the noise-only points and the signal points. But once we get more and more data, it gets a lot easier to separate out only the noise versus noise plus the signal. So this is good. Just an example of what this might look like. So here I'm showing a very strong signal plotted on top of some rather weak noise. And you can see that the output that it recovers when it's searching for both noise and a sinusoid is very accurate. So it's able to reconstruct what was put in very well. However, on the right here, what I'm trying to show is what the sampler is trying to fit when I'm only allowing it to search over the noise parameters. So what it's trying to do is do a very large noise amplitude to try and match the sinusoid that was put in because it can't model the sinusoid. So it's very easy to tell the difference when we have such a strong sinusoid, so a high amplitude. But in the case of a lower amplitude, we can see how it would be trying to balance noise and sinusoid and how it might get confused. So now what we're trying to do over the last few months is we've been trying to use some more realistic data. So we started with the Catalina real-time survey to represent some current surveys and their capabilities. So you can see over here, I have some of the timestamps from a Catalina observation that's taken place, but you can see that they're not evenly sampled because sadly, life isn't perfect and we can't observe the same galaxy every day or every week, at least not yet. But this also makes the searches a little bit more difficult. We're also trying to look to the future. You can see a nice picture of LSST. And what LSST is going to do is take lots and lots of light curves like this very, very regularly. So we're going to have some very densely sampled light curves with lots and lots of data points that are fairly regular. And this is going to help this search, these types of searches a lot. And we're trying to see how it's going to change the possibilities of what we can find. So you can see an example of that here. As we've been working on this, we've been trying to do the exact same model selection. You can see the same plot that I showed before. Again, amplitude versus phase factor. And again, for the more densely sampled light curves, we can see that the noise-only base factors are much smaller and more separated from the rest of this, the light curves in the simulations. So again, more data is going to make this a lot easier. But what we're trying to exactly figure out is how much easier, and what are we going to be able to find that we couldn't find now. So the way we're hoping to do this is exploring which ranges of these different parameters are we really sensitive to for these different types of surveys. And a way that I'm thinking of doing this is shown here. So this is a very preliminary plot. So here I'm showing the amplitude of the sinusoid versus the recovered sigma for the damped random walk. So this is the amplitude of variation. So we might think that these parameters might be related. And you can see that the color around these points is the log of phase factor recovered. And the high amplitude sine waves, we see that they have larger base factors. And this is expected. This makes a lot of sense that it would be able to recover the high amplitude signals. But what we really want to see is, for example, there's a couple of really dark points sort of clustered in this corner. So are there any covariances between these parameters? And this is something that we need a lot more simulations to really narrow down, but this is sort of where we're trying to go. So like I said, we're trying to explore more of these parameter pairs to determine if there are any covariances and what the capabilities, the limitations of this search method are, and what ranges of supermassive black hole binaries we can expect to find. So for example, we might pair up the timescales. So the sinusoid period with the damped random walk timescale, because we might expect those to be related. And we might explore things like the number of cycles in the binary orbit that we've been able to observe. And we're going to do a lot more experimentation with realistic data. So if you're interested in this, feel free to reach out and send me an email or get in touch with us on Slack. And thank you for listening. Bye.